Now, as a second example, let's do something quite different. What we're going to do is we're going to come up with a kind of spelling system or counting system that involves the first 10 digits of pi. Okay, and I've listed those here. Okay, so 3.141592653, those are the first 10 digits of pi. Okay, and so what we'd like to do is we want that as our ending sequence. So after our little spelling routine, we want the cards to be in this order. So you can see the 3, and then the ace is counting as a 1, a 4, ace, 5, a 9, 2, 6, 5, and a 3. Also, what's of interest here is the suits cycle through clubs, hearts, spades, diamonds, clubs, hearts, spades, diamonds, spades. Well, we couldn't have a club here, right? Because we've used it, unless we used 2 decks or something. So we did the best we could. 5 of spades, because that one's still available, and then 3 of hearts. So there's a kind of a pseudo-cycling through the suits, which is kind of curious as well. So this will be our desirable ending sequence. And so we have to figure out, okay, what should the initial state of the cards be so that we can achieve this at the end? So let's dive into the mathematics. I mentioned that more accurately, this should perhaps be called a counting system, because we won't be spelling names, we'll be counting out these digit values. Okay, so here's our desirable ending sequence. Notationally, all of this can be written out in great detail there. X of 1 is 3 of clubs, X of 2 is ace of hearts, and so forth. Okay, so we've identified what the different X sub j values correspond to. The permutation sigma for this card value counting system is the following. Okay, now we haven't derived that in a previous video or in this video, so that is something we need to find. Let's just double check that these are in fact in order, because if they're not, we're going to be off in our permutation. So 1 through 10 looks good. Okay, so what we need to do is we need to go through our card counting system and see what effect that has on the identity sequence 1 through 10. Okay, so this is what we're going to do. Let's go ahead, and if we come back to our, in fact, it's right here. Okay, so these are, in fact, the first 10 digits of pi. So this is something a person could write down, have it on a piece of paper, and people can confirm that, yes, indeed, you've written down the first 10 digits of pi correctly. So what we're going to do is we're going to spell these out, count these out. So 3, 1, 2, 3, and then we're going to put that card down. Sorry about that. 1, so we'll do 1 underneath. 4, 1, 2, 3, 4. Okay, so that's the third digit in pi. The next digit in pi is a 1, so we'll just move 1. The next digit in pi is a 5. 1, 2, 3, 4, 5. Very good. A 9. Ooh. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's a lot of work. 10. No, not 10. Excuse me, 9. The next digit in pi is 2. 1, 2. And then a 6. 1, 2, 3, 4, 5, 6. Excuse me, put that one down. 5. 1, 2, 3, 4, 5. Put that one down. and then we'll put the next one down. Okay. So what we need to notice, and I'll have to just slide this out, if we've done things correctly, we should get the bottom row here. So 4, 6, 1, 3, 2, 10, 8, 9, 7, 5. Okay. So the permutation associated with that card counting system is what we have just found. Okay. And once again, this is in the Cauchy two-line notation. So the magical step is finding the inverse of this permutation. And as we saw in the previous example, that's easily done by just switching the rows. Okay? And I'm hoping that people can see now, why would that be the inverse? The inverse undoes the effect of the original action or the original permutation. Well, why would switching the rows undo the original permutation? Well, it's for the simple reason that here, if 1 is being sent to 4 and we switch rows, we'll have 4 is sent to 1. Combined effect will be 1 is sent to 1. Okay, so that will indeed be the inverse, okay, of the original permutation sigma. Okay, and so that's what we've done down here. I just switched the two rows. And then as before, if you would like to reorder the columns according to the values in the new top row, that would be fine. So here we are, and I just reordered them. So for example, over here, 1 goes to 3. Come over here, 1 goes to 3. 2 goes to 5. 2 goes to 5, and so forth. Okay? So this is the special permutation that we need to apply to our desirable ending sequence D. That will give us the initial sequence ordering that we should begin with before we perform our actions on that sequence of cards. So if we apply this permutation to that sequence, what it does is it permutes these cards, okay? And it's going to permute them according to the instructions in sigma inverse. So for example, sigma inverse of 1 is 3. Okay, so the first card in our beginning sequence will be x sub 3, and then we have to kind of remind ourselves, well, what's that x sub 3? Well, x sub 3 corresponds to the 4 of spades. So that's why we have the 4 of spades first. Sigma inverse of 2. 2 gets sent to 5. So the second term in our sequence will be x sub 5. And then if we match it up here, it looks like it will be paired with 5 of clubs. And so we would get a 5 of clubs here. And so you can go through and check all of these. So here is the new ordering of the subscripts. And then if we go and choose the corresponding physical card, the actual card that's paired with that, we will get this ordering. Okay? So for step 5, what we'll see is that if we begin with this special ordering and then perform our actions of kind of counting out the first 10 digits of pi, we will end with this sequence in which the card values themselves are the first 10 digits of pi. Okay, so let's go ahead and demonstrate that, and then we'll bring this video to a close. In the next video, we're going to some pretty powerful card counting systems that go beyond anything that we've done so far, but it's going to use these exact same 5 steps as we've been demonstrating. Okay, so let's go ahead. So it looks like we're going to need 4 of spades. So let's go ahead and, okay, I think I have built the sequence that we need. So let's just kind of check it here. So I need a 4 of spades, which is what I have. I also need a 5 of clubs. I need an ace of diamonds, 3 of clubs, 3 of hearts, ace of hearts, 5 of spades, 2 of spades, 6 of diamonds, 9 of hearts. Okay, perfect. So the claim is that with this starting arrangement of cards, if we now go through and work with the first 10 digits of pi, something rather surprising happens. Well, you won't be surprised, but anyone watching you do this will most certainly be surprised. Okay, so and how you could present this is you could say, you know, of all the digits of pi, there's actually infinitely many of them. There's no repeating patterns in the decimal expansion of pi. It's an irrational number. But for some reason, the first 10 digits lead to something that's really quite remarkable. So I have these 10 cards, 3, 6, 10 cards. And what I mentioned was the first 10 digits of pi listed here, and we can check that those are correct. For some strange reason, these 10 digits give rise to something very surprising. There seems to be a special harmony among them as digits. So let me just demonstrate this to you. Oh, by the way, you wouldn't necessarily show them all of this here, right? You would just show them on a piece of paper the first 10 digits of pi written out, unless a person has those memorized, which many people actually do. Okay, so this is just for illustration here in the video. In the real world, you would just write out the first 10 digits of pi. Okay, well, the first digit of pi is 3. Okay, so 1, 2, 3. Okay. Ooh, that's kind of curious. Okay. What's the next digit of pi? 1. So 1. I don't know what this is going to be. Ace. Oh, that's interesting. Ace is often associated with the number 1, right? Because come to think of it, there is no 1 in a deck of cards. I guess we could think of the ace as a 1. What's the next digit of pi? 4. 1, 2, 3, 4. What are the chances this is a 4? Okay, what is going on here? What's the next digit of pi? It's a 1. Just move one card. What do we get? That's interesting. We got another ace, which I guess we can view that as a 1. 5. Next digit of pi. 1, 2, 3, 4, 5. 5. Okay. Next one's 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. I can't imagine anyone would be able to keep track of where those cards have been moved after moving the top card to the bottom 9 times. Okay, well, somehow this sequence knows. Absolutely unbelievable. Next digit's 2. 1, 2. Oh boy. 2. Next one's 6. 1, 2, 3, 4, 5, 6. Oh man. 5. 1, 2, 3, 4, 5. You know, if the number had been 4 or 3, we would have stopped on a different card here. It's 5. We got a 5. And what is this last one? It is, in fact, a 3. And there you have it. The first 10 digits of pi in a card counting system in which the number of cards counted and moved led to a perfect reconstruction of the first 10 digits of pi. So there you go. And then as mentioned down, and then as mentioned down here, and I mentioned this earlier, these cards actually cycle through clubs, hearts, spades, diamonds, clubs, hearts, spades, diamonds. This should be a club, but we notice, we can't have a 5 of club in both places unless we use 2 jacks. So I guess 5 of spades we'll have to do, but the next one is indeed a heart. So there you go. So in the final part of this short little series on creating card spelling systems, we will look at more sophisticated card spelling systems, but they will all use the 5 steps that we have demonstrated in this second video. So I hope you'll join me for the third and final video in this short series on card spelling systems.